Slightly more complicated here on example 6. Find the derivative of y with respect to x if x cubed plus xy squared plus y to the fourth is equal to 7. Why is it a little bit more complicated? Because we have a product of two functions inside here. We're going to have to use the product rule in the course of differentiating this thing implicitly. Why do I have to differentiate it implicitly? Because we got a y squared in here. We have a y to the fourth. This is not going to be a function of x. It's going to be at least 1, maybe 2, maybe 3, who knows? Maybe 4. Then determine the points where the tangent line to the graph is vertical. Hey, we've done that before. That's a piece of cake. I'm going to assume that we're going to have a derivative that's a fraction. We just make that fraction thingy, have a denominator that's equal to 0, and make sure the top is not 0 also. Let's try it. Shall we? Shall we? Yes, we shall. So let's see, taking the derivative, on the left-hand side, we'd have a 3x squared. Don't have to use the chain rule on that part. Plus, and now when I take the derivative of this xy squared, remember what I said, we will have to use the product rule on that. Because it's a product of two functions. Derivative of the first, 1 times the second one, y squared, plus the first one, x, times the derivative of the second one, 2y, and now it's y. Implicit differentiation means that I have to multiply it times dy dx. All right, if I was thinking ahead, maybe I could have taken the derivative of that second term and understood, oh yeah, there's going to be 2 here, and maybe just throw it out front. You know what, though? Apple Pencil will allow me to do that really easily. Yep, there we go. Plus derivative of y to the fourth is 4y to the third. Also, it's a y, so make sure you tag your dy dx to the end of it, is equal to the derivative of 7, which is a constant, so it's 0. Notice that we have 2 separate terms that have dy dx's in them, and I'm going to keep them on that side of the equation. And we'll have to factor out our dy dx terms from those. And the other 2 terms, we have to get to the other side of the equation. We'll have to subtract those guys. You know what? I'm going to do them both at the same time. So follow me here. I'm going to go ahead and factor out the dy dx term from these 2 guys. And I would have a 2xy plus 4y to the third left over is equal to, and then just subtract these 2 terms to the other side, a negative 3x squared, minus y squared. Now the only thing left to do is to divide this over to the other side of the equation. dy dx is equal to negative 3x squared minus y squared all over 2xy plus 4y to the third. And we have successfully found the derivative. But we're not done. Why are we not done? Oh my gosh, because we have to find vertical tangent lines. Recap here. Vertical tangent line. It comes from where the denominator is equal to 0. So what I need to make sure I put on my paper is 2x plus y. No, don't put that on your paper. 2xy plus 4y to the third. Make it equal to 0, because the act of doing that's going to get you a point on the free response question on the calculus exam. And who doesn't want an extra point here and there? Okay, now what? We got to try to solve this equation, but oh my gosh, there's x's and y's in it, and this y is raised to the third power. But notice that they both have a factor of y in common. You can factor it out. You can factor out a 2y, actually, so 2y times, I'd have an x plus 2y squared. There we go. And now we act like we're in Algebra 1, applying the 0 product property. I got 2 things that multiply up to 0, so at least one of them has to be 0. So maybe, just maybe, it's this one. 2y is equal to 0, which means that y is equal to 0. Now what do I do with that? Do I want points? Let's see. Then determine the points. Yes, I do. So I need the x-coordinate. How do I find the x-coordinate? I find it by putting that back into the original equation. So plug into original equation. Very common thing that you have to do with these implicit differentiation type of questions. But you know what? You would have done that anyway when it was a function of x. You would have plugged it back into f of x in order to find out what f of x was equal to, right? Right? Of course. Okay, so let's do that. Let's see. We've got, yeah, I can definitely remember that. Let's see. We have x cubed plus x times 0 squared plus 0 to the 4th is equal to 7. I remembered that. I didn't even have a cheat sheet here or anything. Nope. Anyway, so I can see some cancellation happening, and I just have x cubed equaling 7 left over. Take the cube root of both sides, and unlike a square root, you're only going to get one of them. Just one cube root of 7. That's the way odd numbers work, or odd roots work. We know this. We've been in algebra before, which means that we have ourselves a vertical tangent line at the cube root of 7, comma 0. I mean, well, I should say we have one as long as these numbers don't make the top equal to 0. Let's double check that, shall we? So the y-coordinate was 0, so that would be gone. If we were to stick the cube root of 7 in here for x, that is not going to be 0, so we're totally safe. Hooray! And we're not done yet either, because there was another possibility. There was this one. Maybe x plus 2y squared is equal to 0. Huh? Well, now what? You can't factor this one like we could say factor that thing. So what do? We do exactly what we just did right here. I had to plug this value into the original equation. I'm going to do the same thing here, but I got two options. I can either solve this thing for x, subtract over the 2y squared, and then plug that into the original equation, or I can do it with the other variable. We can solve for y and plug the x into the equation. You know what? One of those is way easier than the other one, right? But either way, whatever you're going to do, you're going to plug it back into the original equation. The major difference here is the first time we had numbers to work with, and here we're going to have just literal equations. We're just going to have some variables to work with. It's basically a system of equations that we're solving by substitution. So here we have, I think it was, wait, we didn't actually subtract it over. Subtract over the 2y squared. So x is equal to negative 2y squared. I think I misspoke there. Subtract over the 2y squared. And then plug that into the original equation. My original equation, if memory serves me, is x cubed plus xy squared plus a y to the 4th is equal to 7. Again, right off the top of my head. And we're going to plug that sucker in for all of my x's. Right. Goes in there, goes in there, goes in. No. That made it look like it was going in for y. That's just because I have a hard time matching things up right. Anyway, and it doesn't go into the other one. Let's just do it. Let's just plug it in and see what happens. So I've got a negative 2y squared, which we're going to cube, plus a negative 2y squared, which we're not going to cube, but we are going to multiply it times y squared, plus another y to the 4th is equal to 7. And now let's kind of fix this a little bit. Notice we got an equation that's just got one variable in it, and hopefully we can solve this. Let's cube it. Negative 2 cubed is a negative 8. Y to the, multiply those exponents, 6. And then let's multiply this stuff up. I'll have to add those exponents. I get a negative 2 y to the 4th. Plus another y to the 4th. Oh, we got some like terms going on here, so we can combine those two guys up. Negative 8 y to the 6th. Notice that I am totally running out of space. Is equal to 7. Now what? Well, now I'm going to do exactly what I did on the other example. You remember this one back here? Here, let me remind you. It's like this. Well, not that part. This one here, yeah, we had that cubic equation that we had to solve, so we just plugged it into the calculator to help us solve that thing. Yeah, that's what we're going to do again. But let's get it into a form where we can do that. I'm going to first multiply by a negative. No, I'm going to divide by -1. No, division's too hard. I'm gonna multiply by -1 instead. So I'm going to do that because I like to have that leading term to be positive. Don't know about you. All right, plus y to the 4th, and then it's equal to -7. And then we do need to make this thing equal to 0, so we'll subtract that 7, add that 7 over. Plus 7 is equal to 0. Now, if I'm going to use my graphing calculator to solve it, I have to fool it. I have to switch these y's into x's. So I'm going to type in 8x to the 6th plus x to the 4th plus 7. And instead of equaling 0, we're going to equal it to y and then find x-intercepts, like we did before. And we need the graphing Desmos, of which this is 1. Oh, look, I've already got part of it in here. I wonder why that is. Okay, anyway, so was it plus in x to the 4th? Yeah, let me double check. Yes, and then plus 7. To the 4th, and then plus 7. Whoa, look at this weird looking. Oh, that should have been an x, not a y. How come nobody said anything? To the 4th. And then plus 7. Ta-da! Wait a minute. What the heck is going on here? Notice that no matter what, whenever I zoom, I'm not hitting the x-axis, which means that there's no solutions to this. There's no real ones anyway. But you know what? Could we have figured that out without putting it into the graphing calculator? Well, look. This is an even power, so whatever's going to spit out of it is a positive number. This is the same thing. Positive number is going to come out of this one, plus another positive number. Yeah, that's always going to be positive no matter what. That's why we had that graph of always up above the x-axis. What does this mean? That means that there's no other vertical tangents, because you couldn't solve that one. There weren't any x-intercepts. That's the only one. Well, here, let's take a look at what the graph looks like in this case, shall we? And then we can see right there clearly we have only one vertical tangent line.